Okay, hello everyone, I'm Dominik, I work at Talk, I am also the committer of Apache Aries, and today I would like to talk to you about distributed performance test using Locust. First, let's start with performance test. What is it? This is the way how we can perform, how we can do our test, where we want to check how our system works under particular workloads. And here we want to, for example, check how its responsiveness or stability looks like. We can also check, verify, measure a lot of attributes, especially connected with scalability, reliability. We can also check how our system is using its available resources. And in our cases, we wanted to create and do such performance tests. We wanted to generate a lot of HTTP requests. This is the main protocol how we interact with our tested system. Some of these requests should support SSL. And of course, we wanted to check if all the all the responses from our system are valid in terms of response code, headers, and so on and so forth. And the biggest problem was that we wanted to generate, of course, not in all tests, but in some scenarios, quite big traffic to our system. So it was on the level of 700 gigabits per second. And if you look especially at these numbers, you will see that this is not enough to do on one testing machine. Instead, you need to have some distributed testing environment to do such tests. We also have some other requirements for our system. For example, we wanted to have quite complex scenarios where, because there are several ways how we interact with our system, we wanted to mix them in those scenarios. And we wanted to configure nearly everything in HTTP messages sent to our system to check which, for example, parameters set as the best for getting or interacting with the resources of our system. Most of our clients, users that we wanted to generate, were stateless, but in some situation we also need some stateful clients, which has to know what was the previous request, and based on that, create a new one. We also need intelligent follow redirect. So it means that in our testing system, testing environment, sometimes has to read some external router where the information where some resources are stored, where was the information where some information are stored in our tested system, and we don't want it to measure the request to such external router, only the stuff connected with our tested system and calls to our tested system, no matter how many redirects we have in our tested system. And for our needs, for those requirements, we have found that Locust framework will be the best solution. There are some web pages. First is the main web page of Locust. Quite good documentation is in the second thing. And if something is missing in the documentation of Locust, then everything is open source. And in GitHub repository, there are a lot of very, very interesting things, especially the examples how you can configure your test. Current version of Locust is 1.5.3, and it was even the fourth release of this library this month. So something still going on in this project. The project isn't stale, and the main aim of the whole project is to define some user behavior using a Python code, and with such users, create a lot of such users and swarm our system, our tested system with them. Okay, to start working with Locust, first you need to have a Python in version 3.6 or above. You can take advantage of pip command to install Locust normally, as you do with each other Python dependency, and then the Locust command will be available in your command line. Before we dive into some architecture topics of Locust, let's introduce a quick some terms connected with Locust. We have a master here, master is the only one instance of Locust. We have workers. Workers are that could be a lot of workers, virtually unlimited, of course. On each worker, we are running a lot of users or clients, depending on the place in the system. The name is used interchangeably. And when we want to create new users, then the speed, how quickly we want to create them, is called spawn or hatch rate. And the process of running such users is called spawning or hatching. Okay, and the whole architecture. As I said at the beginning, we have one master and we have some workers. Of course, master knows about every worker connected to it. Worker knows only about master and doesn't have any information about other workers. Communication between master and workers isn't synchronous. In between, we have 0 and Q, so we are exchanging messages on some messaging queues, and everything is asynchronous. The messages that we are exchanging here, that Locust framework is exchanging between those components, could look like that. First, we have some type. Based on this type, we have some set of parameters, additional information that we have to set for such message. And we also have information who is the sender of this message. And at the beginning of the whole life cycle of this of our test, workers have to send client-ready message to master. Master registers it in some registry. Then worker in 1 second interval sends a heartbeat message to master to tell it that it's still available. When the test is about to start, when all the workers are assigned, the number of workers that we wanted to have assigned are already assigned, then master sends a spawn message to worker. Worker acknowledges the message with spawning message and starts creating users. When the process of spawning is finished, then spawning complete message is sent to master. From the beginning of the test, so when the first user is created, worker sends a stats message to master to tell how many requests has been done and what are the response time, what are the times connected with those responses and requests. At the end of the test, master sends a quit message to worker, and this is the message for worker that all the users that have been created during the test should be turned off. And at the end, when all the tests are finished, master could send a quit message to all the workers, and this is the message for worker that there won't be any other tests, and worker could also turn off. When worker sent a quit message to master, this is only the information that this worker doesn't want to participate in next test, but master could still do some tests, but on another set of still registered workers. As I said at the beginning, the whole framework, the whole library is written in Python. So the configuration for all of these components could be written by, of course, in Python. But it doesn't have to be true, because if we have a way how we can communicate with 0 and Q, we have some wrappers, for example, for Java. So we can write our workers using normal Java code. So when it's more convenient for us to write a Java code than Python code, then why not? And our workers are talking with the tested system. And it's very important here on this image to understand that master doesn't have any interaction with the tested system. Only the workers are talking with the tested system. Okay, let's look more deeply at master. To run a master, we have to pass some locust file to locust command. In such locust file, because master doesn't interact with our tested system, it's not really important what we have here. We can have here some dummy user defined, but we have to have at least one user with at least one task defined. So here, as you can see, we can pass a dummy user. In such locust file, we can define a lot of another things, but I will mention them in the future. Okay, when we run Locust in such way, then Locust will expose a web page where you can set number of users to simulate. Also, you can tell what will be the spawn rate and start the test. When the test is started, all the workers send the stats message during the test, and you can find all the statistics in statistics tabs. There is also a charts tab, but charts here are pretty basic. So when you want to do something more interesting, then it's not easy to interact with this web page. So we have started with such a way of running our test, but we quickly changed to another mode of running Locust, and we were running the test using the headless mode. In headless mode, you have to pass the parameters that normally you can pass via web page. So it means users and spawn rate. You don't have button to start and stop the test. So you have to explicitly tell how long the test should be, and also what is the expected number of assigned of registered workers to be registered before we start our test. And based on those parameters, master calculate how to spawn the workload among all the connected workers. So you have to find a balance between all these parameters to create a proper shape of your test. I can give you some advices how to set up those parameters. First, runtime contains a spawn rate times number of users. So it means that if we set certain runtime of the test, then the process of spawning is inside this process. If the spawning isn't finished till finish of runtime, the finish of the test, then the test will finish just quicker, and we do not achieve the number of desired users that we wanted in a configuration parameters. Another piece of advice: our spawn rate should be bigger of or equal the number of users. Number of workers. It means that, for example, we want to generate 16 users with spawn rate 7 on 8 workers. And if you calculate what is the spawn rate for each worker, you will receive a number below 1. And even if master says that it's okay, it is able to calculate such spawn rate for each ready worker, then on the other side, worker could reject such message because it cannot run with so low speed. So you have to have hash rate, minimal value for hash rate for the workers to be run is 1. Okay, another piece of advice: number of users should be equally divisible by the number of workers. What does it mean? If you have 20 users, you want to run them with spawn rate equal 8 and on 8 workers, then you will see that master will tell you that it will run 2 users on 8 ready clients. And if you quickly calculate those numbers, you will see that it's 16, not 20. But if you check your metrics and the number of created users on workers, you will see that in combination, you have 20 users, yeah? And it's because master will send a spawn message with another number of users to generate to some of the connected workers. Some will receive 2, some will receive 3. And especially when you run a test where you don't have a lot of users, then the workload could be not equally divided to all the connected workers, and you should pay attention. If you have really big number of users, maybe it's not a real problem, because one user more on one machine, it's not a problem. But yeah, with much smaller numbers, it could be a real problem. Okay, based on those parameters, the load shape that you are generating, it's linear. And this is the base way how you can create a load shape. In previous versions of Locust, there were also available an option to generate the shape load called linear with steps. For that, you need to pass parameters minus step load. You have to tell what is the number of users on each step to be generated additionally, and what will be the step time, how long you want to spend on that step. And as a result of such parameters, you can create a load shape looking like that. But the problem with those parameters is that if you combine all these parameters in your command line, that they could they could work in another way that you expecting, because here you expect to have 10,000 users, but because of the step time and runtime parameter, you cannot really achieve this number. And yeah, it was the second way how you can create a load shape. And to be more flexible in Locust to run another load test shapes, Locust introduced a class load test shape from which you have to inherit in your test. You can, of course, inherit in your test, and such class will be automatically used by Locust. Of course, you have to define it in master configuration. And in such class, your class, you have to define a tick method which returns a tuple with desired user count and spawn it. And of course, you have access to current runtime to, for example, check in what point in the process you are. And based on those method and the algorithm in that method, you can, for example, create a load test shape where at the beginning you are increasing the number of users very, very quickly to the certain point where you know that your system is stable in it. And after that point, you can create users with slower pace, and then you will be able to, for example, find a moment where your system, for example, breaks. Okay, because we are not running the test in with UI, with web UI, then we have to have some methods to gather all these statistics. Of course, master will print some statistic to output that there is some table, so it's not very easy to parse and use some tools to convert it, for example, to some charts. So there is an option to have reports gathered in some CSV files. If you pass such parameters to Locust, you will have three files, one with the stats at the end of the test, one with the stats history with some intervals during the test, and also one CSV file with failures at the end of the test, of course, if there were any. But still, you have to take these CSV files, do some work with that, generate some charts. So maybe there is easier way to use it and generate charts in some easier way. And for that, Locust also provides very great feature, which are hooks. And with hooks, you can add a listener to a lot of phases, a lot of places in the life cycle of your test, no matter on which side, or master or on worker side. And for example, for us, it was really convenient to start an InfluxDB client in test start when the test was starting. And there we were starting some greenlet, which with 3 seconds interval or something like that, pushed some statistic to InfluxDB. And at the test stop, we were able to turn off such client. And in such way, we have online results of all our tests gathered in one place. Okay, that's all was about master. Let's talk a little bit about worker. To run a worker, you have still to pass a locust file, but you have to additionally tell that this instance of locust will be a worker instance. You have to also tell this instance where is master. Okay, it's not the information where is master. You have to tell where is the master's 0MQ. Yeah, and if you know that connection, this is the only point where you interact with master. In the locust file here, you have to define a real behavior that you want to test. So, for example, you have some. For example, here my user, extending user. User is a class from Locust, and you have to define at least one task here, and you can also define a wait time. As a base classes, you have available user, which is the basic one. You have HTTP user or fast HTTP user, which are great for interaction with HTTP services. Additionally, in examples of Locust, you can find gRPC user, but because maintainers of Locust doesn't want to have gRPC dependencies in Locust framework, then it's only in examples. Yeah, but it's nearly ready to use. You have to just copy paste it to your code. As I said, user have some tasks, have to have at least one task. And here, each task should have some definition. Of course, what do you want to do? How do you want to interact with your tested system? You can set the weight, how often this task should be run amongst all the other tasks. And you can also define tags, which allows you to quickly exclude or include only some subset of available tasks. User also could have wait time, and there are three wait times built in, wait times function built in. You have between, where you can set a number, where Locust will get some number, will randomize some number in range from 2 that you set. Of course, the time is in milliseconds. You have a constant. It means that this is the time from end of previous task and start of the next task. And you have constant pacing, which is the time between beginning of the previous task and starting of the next one. And very important information connected with wait time. Without wait time, you cannot easily predict RPS of your system because Locust will just run the task one after another without setting wait time, without any waits. And as I said, we used Java worker. Our workers were written in Java. And for that, you have two libraries that I have found. One is Locust4j. It's pretty easy. The most focus of this library is how to interact with ZeroMQ. So the last release was on 9th of March 2021, because then the way how you communicate on ZeroMQ has changed. And there is additional library called Swarm. But the problem with that library is that it's nothing really changed in that library since 13 May 2020. So we are pretty happy that we have chosen Locust4j as a base library for our Locust workers. Okay, you have a master, you have a workers, but you also additionally have to have some supporting architecture to run everything in your environment. So as I said at the beginning, you are starting with master, you have some workers, in our case, Java workers. We have very complex scenario which we wanted to run on in such tests on the worker side. So we have YAML files which we wanted to distribute amongst all the workers to tell them how they should act during the test. We were gathering statistics from master, and as I said during the reporting part of the presentation, we are sending some metrics from master to InfluxDB and Grafana. Such metrics were response percentage, RPS, request count, user count, errors count, average content length. This is the variables, this is the statistics available and calculated by master, gathered and aggregated from all the connected workers. But in the situation when we run a distributed test, performance test, or even any other performance test, we have to look how our workers and its machines look like. What are their statistics? And for that, we have installed Jolokia on each JVM. And from such Jolokias, we were able to expose some metrics via JMX and make them available via HTTP. And then we also have on each worker machine installed Telegraph, which were able to gather the statistics from Jolokia, from HTTP exposed by Jolokia, and also from operating system, and also send such metrics to InfluxDB. And yeah, from worker JVM, we were gathering information about garbage collectors, memory usage, threads. From worker machine as a whole, we were gathering information about CPU usage, memory usage, or network usage. And based on those statistics, we were able to monitor how our working environment looks like and how it works during the test. Of course, if you want to install all these components, you have to some orchestrator. For us, it was no, there wasn't a better solution than Ansible. We have used Ansible to install whole stuff and also to configure the test and run the test during some sessions. If you want to use Ansible, you have to create an inventory file with definition where something has to be installed and where something is already on some connected machines. So our Locust master was on certain machine. On the same machine, we have installed Grafana and InfluxDB, and we also have a set of workers machines where we have where we can have a lot of instances of Locust installed in the same time. Why we installed a lot of instances of Locust on one machine? It's because we need some scaling of those workers, and it was connected with that all the workers that we have, I mean worker machines, weren't the same. We have the number of processors in nearly every machine was quite the same, expect one machine, but the network bandwidth were from 20 gigabits per second to 80 gigabits per second available on each machine. And based on that, we wanted to distribute the workload amongst those machines and use most of the resources available on each machines. So based on those information, how the machines look like, then we have to calculate that, for example, when we wanted to perform some tests, when we want to generate big network throughput in the test, one worker could be virtually assigned to 20 gigabits per second network card or 10 gigabits per second. When we wanted to create a test where the key was the number of connections, especially HTTPS connections to our system, then one worker could be virtually assigned to 8 processors, maybe 4 processors, depending on the load that we wanted to generate. We also wanted to distribute the number of workers amongst all the number of users on each worker, so do not have a lot of them on one JVM. So we have to look, for example, how many users we are able to run on one instance of worker. If we don't use these, if we scale in a wrong way, then, for example, the CPU usage on our workers could be top out much quicker than on other machines. And in such situation, the results of our tests could be just thrown away because we were more testing how our testing environment works under such workload, not our tested system. Especially with CPU usage on workers' side, we should be able to achieve about 80%, 80 to 90% CPU load on the workers' machine. If we achieve more, then probably this is some problem with our environment and we should rescale the whole test. Okay, let's come back to the testing process. First, when we wanted to start our test, we have to install everything. And for that, we have Ansible and we have a certain playbook to run such installation. When the installation was finished, we were able to release the Locust. For that, we have another playbook called run yum. And here we can define number of users to generate, hatching rate, also the time of the test, how long the test should be, and those parameters are passed to master. We also have a parameter where we can define where is the path to the scenario that we want to run during this test. Yeah, and the life cycle of such tests look like that. First, we start with the locking the whole environment because we don't want to share our environment with someone else, and someone could want to run a test in the same time as we. So we don't want to share the resources. Then, when we lock the environment, we start a master. When master is started, it reports that it's waiting for connected workers, and number of workers were calculated based on the number of instances to all workers on each worker's machines defined in inventory. When master is waiting, then we can distribute the scenario file amongst all the workers, and then we can start telegraphs and workers instances. When we do so, master will start to receive information that such workers are ready, and it will count. You can see the progress and for example, check how quickly your new workers are assigned to master. And when all the workers are already ready for the test, and master starts the test, it sends a spawning request, spawning message to all the workers calculated for each worker. And when we do so, then the only thing that we can do now is waiting for test to be finished. In meantime, of course, we can look at Grafana charts and check what's going on, how our system and our testing environment and our tested system look like. Master also prints some statistics. This is the basics one that you can find. Also, at the end of the test, master will print some percentage for each task that we have been using during the test, and master will at the end also turn off all the workers and turn off also itself. But in our framework, in our playbook, we explicitly also stop master and workers, and of course also telegraphs and release log, just to be sure that everything is turned off. Additionally, we also have a kill playbook, which allows us to turn off the tests no matter what happened. For example, we calculated the number of users in a wrong way, or the shape of our load test isn't expected, then we can just stop the test and run it again in a moment. Okay, and during the test, we have found some problems connected with Locust. Pretty annoying problem at the beginning. There was some missing messages at the beginning of the test, especially at the beginning of the test. We haven't found missing messages next in the future, but at the beginning it was some problem. And here, let's imagine all workers are started, but master doesn't receive client-ready message from one of the worker that we know that is running. And in such situation, master waits forever. Of course, we have some wait times implemented in Ansible, but this wait time was in minutes, not in seconds. Yeah, and master will report that it's waiting for one connected worker to be ready. There is no point for looking which one worker didn't connect. Instead, when you have a big number of workers, just restart all the workers and run the test again. Another problem that we had is a problem with missing failures in Locust metrics. We knew that something bad happened during our test. For example, we have seen some errors in our tested system logs, also in metrics of our tested system, and in some logs of our workers. But on master side, in metrics gathered by master, we haven't seen failures. And the problem was that from Java, and we were able to send statistics to, not send, to gather the statistics using two methods, record success and record failure. And the problem is that the queue connected with record failure is consumed much slower than record success because you have to calculate some additional stuff connected with errors. So to fix that problem, and see all the metrics in our statistics, we can of course wait for failures to be consumed from the queue, sent to master, and everything should be fine. But then you can lose the correlation between times when something happened during the test and the real time. So instead, you can use record success to report failure. And for us, it was convenient because we have added, for example, some prefix to the API of Locust that we are able to use. And because we had a hook on master, we were able to take this message and check if it contains some certain suffix. And for example, based on that, sends metrics to InfluxDB with some additional tags telling that this statistic, this data are not about the successful responses, but about some failures. Okay, another problem that we had, and it's a problem with task order. Let's imagine we have 60% of task A to run and 40% of task B to run. We want to run 1,000 users, and we will see that Locust first will start 600 users of task A and then 400 users of task B. So if you have two tasks on your chart, first you will see only one, and then the next one will be growing. And the problem is that in normal scenarios, in normal system usage, such workers, such tasks by workers should be generated from the same start point, yeah, and should increase, of course, with the proper weights, yeah, but from the same point of time. So for us, solution for that problem was to randomize tasks on ourselves. We don't have a strict number, 60 to 40%. We have 59 or 61 connected with the first task, but it was okay for us. Statistics works quite good in such situation. Another problem, which it wasn't a big problem for us, but it could be a problem for you, depending how you want to write your test, is a response time bucketing on Locust side. Here, Locust maintain a dictionary response time to number of occurrences of such response time, and to save memory and also to save a space, to make a smaller messages exchanged on 0MQ, such response time are rounded. And depending in what place in code you can look, you will see that in one place such buckets are described as you can see on this slide. In other place in the system, you can find another example, and to check how it works in a real test, you have to find a proper code which handles that. Yeah, and here you can check that the buckets are pretty big, and it won't be a problem for you, especially when you have very short tasks to generate, to interact with your tested system. But in some situation, when you want to measure very long tasks, you won't have an exact time for each of the tasks. So there is no point measuring if you gain some speed and before you have a task ended in about 3 seconds and 15 milliseconds, and after some optimization you have 3 seconds and 5 milliseconds. It won't be visible in your results because of such bucketing. Another problem that we had was connected with the JVM problems. We have when we are using JVM, we have garbage collectors. So we could have some problems with garbage collecting, especially when we are creating a lot of objects, and we can have stop the word phrase somewhere in our tests. There is also we have JIT, which optimize our code just in time. And there could be some peaks, especially at the beginning of our test, because you don't have a special warm-up phase in during our tests. And because we are running a lot of threads on this JVM, there could be a problem with too many threads and context switching between those tests. To solve that problem, don't create unnecessary object. Measure only the necessary task part of your interaction with your tested system. Don't create such critical section too big. Use more worker instance to distribute the workload amongst more JVMs and be able to survive problems of one JVM. And monitor constantly JVM metrics of your workers to check if something when something appears in charts of in the result charts of master is a problem of your workers or problem of your tested system. The last problem that I want to mention is problem with breaking changes. We have found that maintenance of Locust doesn't use semantic versioning. So when going to version 1.3, in release notes, we have only the short information that this release contains breaking change and deal with it, yeah? So when you want to run Locust, use Locust, read carefully release notes before any upgrade because something could be just turned off from your code. Okay, that's all from me. If you have any question, this is the perfect moment.